So, yeah, so the idea of this next bit is just to play around a little bit more with these equations. The first bit you should kind of know, sort of where these equations came from, what the assumptions are behind it. This next bit is a little bit more complicated. I'm not saying it won't come up in sort of the assessments and stuff, but you'll be sort of guided through it a little bit or whatever. So this is, I'll go a bit faster as well. I won't sort of try and explain every line in quite so much detail for this bit. But this is just exploring the ramifications of this set of assumptions that we've made and seeing what they would tell us about materials. And essentially, we're going to bump up at the limits of what this model could actually do for us fairly quickly. Right, so essentially, even sort of quite early on, the ideas were, well, how far can we push this classical model? What would it tell us? And let's go beyond just adding a static electric field, just sort of putting a couple of electrodes over our material. Let's actually see what we could potentially measure. Can we actually get to grips at what this tau is? Can we extract things like this electron density by making some clever measurements? So if we extend our external force, our applied fields, to not just the electric field, but also the magnetic field, then we have the full Lorentz force expression. So the electrons will be not just accelerated down the potential, but they'll be sort of swerved off to the side by the magnetic field. So our equation is going to look like that. We can do a similar job to we did the last time. If we let's just have a static electric field and a static magnetic field for now. So just a constant, non-time varying one. And then the same argument as before, we'd expect the system to settle down into some steady state with electrons moving on average with a steady sort of drift, a steady flow. So we will assume that the right-hand side is equal to 0. So we've got that equation there. So we're substituting in our relationship between the velocity of the particles and the current in the system. So essentially it's this linear relation that the current and the velocity are related by the density of electrons and the charge on the particles. So we plug that in, get that equation at the bottom, and if we rearrange and get the electric field on the left, here even, we've got a more complicated, sorry, I did start. We've got a more complicated expression linking the electric field to the current in the system. It's a bit more complicated because the magnetic field is there as well as the electric field. I'm not going to go through all the steps here. I'll leave it to you to check. But what we can do is that we can work out from this formula a proportionality constant between the electric field components and the current components. So we can expand this cross product we can write out what this cross product is in terms of components of the current and components of the magnetic field. What's B actually called? I always forget what it. It's not that it's H field. This is some. I'm going to call it the field. I know some fussy about calling it something different. It's the magnetic field, as far as anyway, what you can do, I'll just tell you this, is that you can write this proportionality between the electric field and the current in terms of the current times some matrix. So this 3x3 matrix. It's called a tensor for being fancy. So essentially, what it means is that the electric field and the current, when we've got a magnetic field in this system, are no longer directed in the same direction, because the magnetic field is sort of making the drift of the electrons curve. It couples the perpendicular direction to the electric field. So what we could do is we could write out the components of this, and then we could compare the x component of the electric field, the x component of the current, and we find that the first index, if you like, basically there'll be three terms that could be induced due to the electric field, the thing accelerating it along the x direction, but then also a magnetic field along y or z would also cause it to accelerate. So if we wrote out those things component by component, we could work out which things made up each of these elements in the matrix and write them down. So, questionnaire. Essentially, if we were to only have a magnetic field along the B direction, then we would have this kind of relationship there. So the diagonal element is essentially the electric field. So if we apply an electric field down those different directions, so if we apply it down the y direction, we get current in the y direction. It's given by our proportionality that we worked out before, tau and e squared and all that business. But off diagonals gives us where the magnetic field along the z direction will accelerate a current along the x or y directions. And you can define something called the Hall current, the Hall coefficient, which is essentially this relationship between the electric field and the current induced by the magnetic field along the perpendicular direction that drives it. So that's this element here off the main diagonal, so it's not coupling the same component of the electric field and the current density. That one. If we normalize it or divide it by the strength of the magnetic field that we apply, divide by this, we get it to -1 over this product term. One is the electron density in metal, and the other one is the charge on the electron. If we already know the charge on an electron, this means that by making a Hall effect measurement, we can measure the electron density in the material. The exact details where you got these bits and pieces from may be a little bit fiddly, but the basic idea, I hope, is reasonably there. So the magnetic field will cause an acceleration perpendicular, which means there's kind of a resistance or a coupling between the current in that direction and the electric field. If you set up a nice geometry, some of you may have done the Hall effect measurements, or will do it this turn maybe. So one of the things you can extract is actually this electron density material. I'll say it again in a minute, but the other thing, the relationship between, if you don't apply a magnetic field but just a potential, a constant electric field, we should induce a current that's related by this expression, which has got the electron density and the electron charge and mass, which are known, and this tau. If we do a Hall measurement, we can measure N, the electron density, and if we make a measurement just without a magnetic field, we can extract something that's got the product of N and tau, so we can extract tau. So by doing these series of measurements, a DC electric field and then a DC magnetic field in the right geometry, we can measure the electron density independently from other things in this model. And then once we've got the electron density, we can work out what the product of the electron density and tau is, so we can extract what tau is in our model. So then we've got our parameter for our model, and we've got the electron density in the metal, and we can see whether they make sense. I think these are just words more or less same as anything as I just said. So there's this magneto-resistance, called magneto-resistance because it's coupling the current and the electric field in different directions, caused by the magnetic thing. So it acts like a resistance in a traditional sense, but in and off between different elements of the field. And some things to have a little think about. I want to hurry through and stop there. But the rather important thing here is that the Hall effect will depend on the sign. I'll show you some numbers later that actually imply that quite often, instead of electrons with negative charge, you make these measurements, and what comes out is that you get a Hall coefficient with the wrong sign. Kind of implies that we've actually got a positively charged electron carrying the current in these materials. So that is probably the number one thing that suggests that this model is complete. If we carry out these measurements on some material that is happy, doesn't lead to any complications, then we get that the scattering time, this tau, comes out about 10 to the minus 13 or 14 seconds. Say that this tends to correspond to maybe microwave into sort of infrared sort of regions. So it tends to correspond to vibrations in the material. think I'll skip this now in the interest of time. But you can extend this model not just if you apply a stationary electric field, but if you include time varying electric field, you can follow through the consequences on the current, on the response of the metal. So just very quickly, don't worry if I'll show you some of the details first. So if we apply a time-dependent electric field, so this electric field varies with time, essentially as cosine omega t. So if you remember this De Moivre relationship, that complex exponential is equal to sine x, cos x plus I sine x. The real part of this thing here is equal to some number times cos omega. If we assume that is our that's the electric field we're going to apply, plug it into our equations. I do just like that. And then we assume that the electrons are going to kind of join in the dance. They're going to go backwards and forwards in a similar way to the electric field that we're applying. We can plug these into our Drude model. Our derivative on the left-hand side is dp by dt. This gives us an I omega out the front. Then we can cancel out the rest of our exponentials. And yet again, we can find a proportionality between the current and our strength of our electric field that we're applying to the material. But now there's an additional complication, that the proportionality between the current that's induced and the electric field that we apply is no longer just this sort of straight number dependent on the material, but it depends on the frequency of the AC, of the light, of the electric field that we're applying. And we've got an expression for the proportionality constant, just the conductivity. And again, it depends on these familiar sort of Drude numbers, its electron density with scattering. And I'm going to definitely skip through this. But what it actually implies is that from this relationship between the expression for the current and the electric field, if we plug it into the Maxwell equations and do some manipulations, a little bit of algebra, we end up again with a expression linking the propagation of a electromagnetic wave in the material to these same properties related again to this conductivity theory. This gives a prediction for how a metallic system with these Drude electrons in it absorbs light. absorbs electromagnetic radiation. These different frequencies. You can take this Drude model quite a long way, even though it's a relatively simple model in terms of just what we saw of the setup. Essentially, the important points about this model are that below something called the plasma frequency, metal absorbs light very strongly, which also causes it to reflect and to be shiny. But there's a frequency called the plasma frequency, and above that limit, the metal no longer absorbs light and can actually transmit essentially we just let light straight through. The frequency in this model above which the metal is only transparent, which ends up being kind of correct. I can definitely skip that. Leave that for another day. Now, I want to sort of accelerate. I'd recommend having a flip through a textbook going through this after I've finished. You can see there's quite a lot of sort of similar sort of material. It's all following the same idea. It's a classical particle. We apply a field. We see how it accelerates. We work out how many particles, what charge goes through the material. So after considering the electrical properties, how much current is carried by these materials, you can consider other things. So you can consider thermal transport. So how much heat would these electrons flying through the metal actually transport? I'm going to skip through them. But what you can do, you can assume that each particle is going to carry a certain amount of heat of the order of kT. Comes from the sort of the heat capacity of them. You can plug that into the heat equation. Again, it's the same thing. We've got our expression for the velocities. We've got the equation. We take our average velocity from the Maxwell-Boltzmann distribution for classical gas, plug it in, and we get our proportionality, this thermal conductivity. So this is the proportionality this time between the thermal current and the temperature gradient. Again, I don't want to go into the details here. I'm just going to pick through it. It's basically the same thing. So instead of seeing how much charge goes through a surface, you see how much energy goes through a surface. Again, it's counting those particles. It's using a similar expression for the velocities of the electron and this assumption about how much energy each of them will be carrying from the Maxwell-Boltzmann distribution. And this kappa again is this proportionality between the current and this time the temperature gradient instead of the potential gradient electric field. And what you get in the end, just take the result, that the proportionality between the thermal current and temperature gradient is given by this expression. Again, it's got this n and tau in it for this electron density and this scattering time for the same reasons as before. And what you can define is a so-called Lorentz number, which is the ratio of this thermal conductivity to the electrical conductivity. And most of these coefficients, all these parameters and stuff, drop out of this. They cancel out in our model between kappa and sigma. So that's the electrical conductivity we worked out. This is thermal conductivity. So most of the parameters here cancel out. So this measurement should, in our model, give a constant value no matter what the material is. So the tau does depend between different materials, but the ratio between the thermal and the electrical conductivity should stay the same in this model for all materials. And it doesn't. It does work reasonably well. There are a decent number of materials that actually give the right ballpark. You know, frankly, it's a bloody miracle it gives anything at all. But it does work reasonably well. But there are quite a lot of materials where it really doesn't work out at all. Where have I got the numbers? I'm going to skip this. There's other things you can do, coupling of heat and electric current. It's the same game, but you just repeat. There's this so-called Seebeck coefficient, which is the relationship between this thermal and electrical current. Again, it's related to that thing that I've just talked about. Again, this prediction that comes out from the Drude model. Again, it predicts something called the Seebeck coefficient that should be independent of the material. That's similar to the previous one. Again, I think Seebeck coefficient is something you may measure in labs if you're doing that. So this should give a constant number. I think platinum is picked as a number that's, relatively speaking, of the right ballpark to there. But then, so within our model, this every time you measure S, no matter what the material, you should get the same number. But in fact, we get about 4 orders of magnitude variation or something like that across the different materials. So there are a good number of materials where we get something ballpark, you know, we've got the right order of magnitude, but in fact it can't explain what's going on across different materials, and it can be grossly wrong. So what I wanted to get to in the end, get some better examples up there. There's definitely, if you look into the textbooks, they'll have many more examples of these failures. But essentially, the big ones are this Hall coefficient, so this thing, this resistivity of a material, conductivity of a material that when you apply a magnetic field to it, the Drude model says that would be electron density. The density's got to be a positive number times the charge of the particles. And most of the time this comes out with a sign and a magnitude that sort of makes sense for an electron density and an electron carrying a negative charge. But there are a good number of materials where it comes out with the wrong sign. So we appear to have some magical positively charged electrons in some materials. The bit I skipped through, this dielectric function, is much too simple. So this is how electrons interact with AC fields. So we came up with an expression that linked the applied electric field to the absorption of it. And this had been absorbing quite strongly up until some cut off where it just stopped and the field became transparent. And this is much too simple for real materials. Definitely a lot more going on. take actual experimental data of how they or how to do PC pipeline. I didn't touch on this, but the heat capacity of electrons is grossly overestimated by this model. And the mobility of electrons is grossly underestimated. So I said this ratio of the thermal to the electrical conductivity quite often comes out about right. But if you dig into it a bit more, you find that this ratio works out because the electrons are carrying a lot less energy than our classical model expects. But the ones that are there are travelling way faster than we would expect, classically. And this thermal power measurement, this ratio of the electric current to the heat current is off by a factor of 100, which is back to this point about the amount of heat capacity of these electrons is off by a large amount. So why have I whittled on at you about all this stuff? So it's important to try and get the impression that you could do quite a lot of stuff with classical theory. You could come up with some model for a metal that would even explain sort of why it would absorb light. It would give some reasonable, even semi-quantitative measurements or results for some materials. And within some reason, it can give you some quite good sort of ideas like this Hall measurement, even that can be used for quantitative work. But if you look too closely, it breaks down, and it breaks down in multiple places in quite subtle ways. And I think the big problem is there's no real easy or there's no practical way of improving this classical model. People tried all sorts of refinements, making more complicated scattering coefficients and all that sort of thing, but it doesn't really change the results in any significant way. Essentially, you've got to get away from this classical model and go to a quantum model. And the first things that the quantum model will allow you to do are to explain why you could get some electrons that appear to have positive charge in the material. We'll be looking at that quite soon. And the other thing is dielectric function. So this, whether it absorbs AC applied electric fields, as in light. This model means that all materials will absorb light up until some frequency. So it would have basically all materials being metallic and being shiny up until some frequency at which they become transparent. And that's just not an accurate representation of the world. And again, having quantum mechanics, essentially putting in energy levels, particular allowed energy states, will allow us to solve these various problems. So that's the end of today's material, and what we will be doing over the next 2-3 weeks is putting in the equivalent quantum mechanical picture and seeing how they compare and seeing how the quantum mechanics fixes up that thing. So hopefully at the end of that we'll have at least a reasonable picture of what electrons in real materials look like, how they behave and why the quantum mechanics is needed. Right, that's it for today. I'm not going anywhere. I mean, questions and stuff are welcome, but that's me talking at you done.